On February 27, 2026, engineers at NASA's Jet Propulsion Laboratory sent a routine command to Voyager 1, a spacecraft nearly 15 billion miles from Earth, instructing it to perform a maneuver it has carried out countless times before, a simple, controlled role designed to help calibrate one of its remaining instruments. It's the kind of operation the mission team has executed so many times over nearly 50 years that it barely qualifies as newsworthy. Except this time, something happened that nobody on the ground had planned for. As Voyager 1 rotated, its power levels dropped unexpectedly by an amount the team hadn't anticipated, pushing the aging spacecraft dangerously close to triggering an automatic safety system that could have shut down critical components on its own, with no engineer anywhere near enough to intervene in time. And what caused that unexpected drop has never been fully explained, and the response to it, decided in the weeks that followed, permanently silenced one of the last two functioning scientific instruments this nearly 50-year-old spacecraft has left. To understand why this moment carries so much weight, you first need to understand exactly what kind of position Voyager 1 is in right now, in the summer of 2026. Launched in September of 1977, on a mission originally built to survey Jupiter and Saturn over a handful of years, Voyager 1 has been operating continuously for almost 49 years, decades beyond anything its original engineers ever expected. In 2012, it became the first spacecraft in history to cross the heliopause and enter true interstellar space, and it has remained there ever since, sending back data from a region of the galaxy no other functioning instrument has ever directly sampled. But that longevity has always come at a cost, one that grows sharper with every passing year. Voyager 1 runs entirely on radioisotope thermoelectric generators, devices that convert the heat produced by slowly decaying plutonium into usable electricity. That decay never stops, and it never reverses. Each year, the spacecraft loses roughly 4 watts of available power, a small, steady drain that has been quietly, relentlessly shrinking Voyager 1's operational capacity since the day it launched. Managing that decline has become one of the central, ongoing challenges of the entire mission. Of the 10 scientific instruments Voyager 1 originally launched with, 8 had already been shut down by early 2026, each decision made carefully, years in advance, by a team forced to weigh the value of every remaining watt of power against everything else the spacecraft still needs to survive, including the heaters that keep its fuel lines from freezing solid in the deep cold of interstellar space. By April of 2026, only 2 scientific instruments remained active: the plasma wave subsystem, which listens to the electrically charged particles surrounding the spacecraft, and the magnetometer, which measures the structure and strength of the magnetic fields Voyager 1 is currently moving through, fields that, remarkably, still show measurable influence from our own sun's magnetic field, even this far beyond the heliosphere. The magnetometer is exactly why that February roll maneuver happened in the first place. To properly calibrate that instrument and separate the spacecraft's own faint magnetic signature from the actual surrounding interstellar magnetic field it's trying to measure, Voyager 1's engineering team periodically commands the entire spacecraft to physically rotate, a maneuver that lets them isolate and subtract out Voyager's own internal magnetic interference from the readings. It's a routine, well-understood procedure, one the mission has relied on for years without major incident. On February 27, 2026, the team sent that same familiar command. And as the spacecraft executed the roll, something unexpected happened. Its power output dropped by more than engineers had planned for, more sharply and more suddenly than this kind of maneuver had ever produced before. Here's why that mattered so urgently in the moment. Voyager 1 carries an automated safety system called undervoltage fault protection, built specifically to detect a dangerous drop in electrical power and respond by automatically shutting down onboard components to protect the spacecraft from more serious damage. Kareem Badarudin, the Voyager mission manager at JPL, later compared this safety system to a trapeze artist's safety net, present for exactly the moment things go wrong, but never something you actually want to have to rely on. If Voyager 1's power had dropped any further following that roll maneuver, the fault protection system would have triggered automatically, shutting down components on its own without any input from the ground, and forcing engineers into a lengthy, genuinely risky recovery process, made even more difficult by the simple fact that any command sent to Voyager 1 currently takes over 23 hours just to arrive, with a response taking another 23 hours to make the return trip. A problem that might take minutes to diagnose and fix on a spacecraft in Earth orbit can take weeks to properly resolve on a machine sitting this far from home. Rather than wait and risk that automatic safety system triggering on its own, the mission team made a difficult decision in the weeks following the incident. On April 17, 2026, engineers at JPL sent commands to permanently shut down the low-energy charged particles experiment, an instrument that had been operating on Voyager 1 almost continuously since the spacecraft's launch in 1977, measuring the ions, electrons, and cosmic rays flowing through the solar system and the surrounding interstellar medium for nearly the entire duration of the mission's incredible, decades-long life. Badruddin was candid about how the team felt about the decision, saying plainly that shutting down a working science instrument isn't anyone's preference, but that under the circumstances, it was simply the best option available to protect what remained of the mission. Voyager 1's twin, Voyager 2, had already lost the exact same instrument roughly a year earlier, in March of 2025. As part of the same, ongoing, carefully managed power conservation effort both spacecraft have been undergoing for years. Now, here's the part of the story that deserves genuine attention, because it's the piece that never quite gets a clean, satisfying answer in any of NASA's own public statements. What exactly caused that unexpected power drop during a completely routine roll maneuver, a maneuver the mission had safely performed many times before without incident, has never been publicly detailed with a specific root cause. NASA's own communications describe the sequence of events plainly and honestly: a planned maneuver, an unexpected drop in power, a decision made to act before the spacecraft's own automated safety system forced a riskier outcome. What isn't included anywhere in the public record is a clear technical explanation for why that particular roll, after so many uneventful ones before it, suddenly produced a power drop nobody on the mission team had modeled or predicted. For a 50-year-old spacecraft running on a slowly, predictably decaying power source, an unplanned deviation like that is exactly the kind of unresolved detail engineers take seriously, even when it doesn't get resolved with a tidy explanation in a press release. The reality is that Voyager 1 is now old enough and its systems worn thin enough that its behavior has genuinely become somewhat less predictable than it once was, a natural consequence of running any piece of hardware for nearly half a century, tens of billions of miles beyond any possibility of physical repair or inspection. Every component on board has been continuously exposed to the harsh radiation environment of deep space for decades, and small, cumulative effects on wiring, on internal circuitry, on the delicate balance of power distribution across dozens of interconnected systems, can eventually produce exactly this kind of unexpected, imperfectly understood behavior. It doesn't necessarily point to any single dramatic failure. It points to the simple, sobering reality that this spacecraft is now operating well beyond any scenario its original 1970s engineers ever designed for, held together by careful, ongoing management rather than any illusion of full, complete predictability. And yet, even after this setback, the mission isn't simply coasting toward a quiet, resigned ending. NASA engineers are actively pursuing an ambitious, genuinely experimental fix, informally nicknamed the Big Bang procedure, designed to restructure how power flows through the aging spacecraft's remaining systems in an attempt to squeeze additional usable electricity out of components that aren't currently operating at full efficiency. Because any change to a 50-year-old spacecraft's power distribution carries real risk, the team made the deliberate choice to test this procedure first on Voyager 2. Which currently has slightly more power margin to spare and sits somewhat closer to Earth, making a potential failure less catastrophic to the overall mission. Those tests were scheduled for May and June of 2026. If they succeed, the same fix will be attempted on Voyager 1 sometime no earlier than July of this year. And if that attempt works as hoped, there's a real, if still uncertain possibility that the very same low-energy charged particles instrument shut down back in April could eventually be switched back on. All of this is unfolding against the backdrop of an approaching, genuinely historic milestone. On November 18th, 2026, at 2:16 and 7 seconds in the morning, Pacific time, Voyager 1 will reach a distance of exactly 1 light day from Earth, over 16 billion miles away. So far, that a radio signal traveling at the absolute speed limit of the universe will need a full 24 hours just to arrive, and another 24 hours for any reply to make its way back. No human-made object has ever been that far from home. Voyager 1 will cross that threshold while still alive, still transmitting, still managed by a small, dedicated team of engineers on Earth, making increasingly difficult, increasingly consequential decisions about how to keep a 50-year-old machine functioning at the very edge of what any spacecraft has ever been asked to endure. That's the real story behind what happened this year. Not a dramatic, otherworldly discovery beamed back from the edge of the solar system. Something quieter and in its own way more affecting. An old, remarkable machine, still faithfully executing a routine command it has carried out countless times before, suddenly behaving in a way its own engineers hadn't fully anticipated, forcing a difficult, unwanted decision, made carefully from a control room 15 billion miles away, by people who have spent years, in some cases entire careers, trying to keep this specific spacecraft's voice from finally going quiet. Voyager 1 turned, as instructed, exactly as it always has. What happened next is a genuine, still not fully explained wrinkle in the long, remarkable story of a machine that was only ever supposed to last 5 years, and is now, nearly 50 years later, still finding new ways to surprise the very people who built it. If stories like this, the quiet, real, and genuinely unresolved moments behind the headlines, are what you come here for, stay close, because there is more still unfolding 15 billion miles from home.